Good morning. Today we start on the last topic in this course. It's Bayesian deep learning. It is how to use the Bayesian methods that we studied throughout the course for the purpose of deep learning. So this today's talk is heavily borrowed from the ICML 2020 tutorial by Andrew Gordon Wilson of New York University. So it's heavily borrowed from him. You can also go through his talk that is available in YouTube. Okay, so all of you, I think you know that those of you use neural network or use any machine learning algorithm, you know that deep neural networks are pretty popular. And the steps are as follows. You have a training set and there is some particular task mentioned. For example, you have to recognize an image, categorize an image. You train your network, which basically means that using gradient descent, that is the backpropagation algorithm, which minimizes the error function, some cross entropy or mean square error, some error function or classification error, some error function you minimize and find out the optimal set of weights. And using this optimal set of weights, you predict the output for a new input. So you just use this optimal set of weights to predict the output for a new input. And so this works fine. This works very much. But the point to be noted is that for a given input, there is only one single output. So if you give the image of a say cat, its output will say only cat, nothing else. It will give a single output. And the final set of weights that we obtained after the training iterations are over, basically the optimization process is complete, are only point estimates. So that is, which basically means that you have a single set of values of the weights after you have finished your training. So deep neural networks are very successful in several talks like face recognition, speech recognition, text mining. But there are some questions which are yet to be answered if you want to use such deep learning systems for safety critical applications. Say for example, autonomous driving or medical diagnosis. And these questions are the follows. That means you have used a deep learning algorithm, but how confident are you about your prediction? Because in many safety critical applications, you really need high confidence predictions. Also, are there any gaps in learning? So that means, is there some part of the real life input which is not covered in the training set? And so the network has not learned that part of the input, that part of the input space. So is there any gap in learning? Secondly, that is the learning complete? That means, do we have a good, reasonable, confident prediction without gap, or we need even more training data to really use it in practice? Also, there are some theoretical questions that are unanswered. For example, deep learning algorithms have been found to work even for relatively small data sets. But even though the number of parameters in a really deep learning network are very, very high, in millions. And usually the philosophy in machine learning is the number of data points should exceed by large the number of parameters, but the reverse happens here. So this problem is known as the over-parameterization problem. It usually should lead to overfitting, but often it doesn't happen. So why does, so basically, why does deep learning work, even though it has a huge over-parameterization? So these are some of the questions, and some of these questions, not all, it can be solved using Bayesian learning. So we try to address the following limitations. For example, the limitations that the output is a point prediction. So there is no quantification in the uncertainty of this prediction. So how confident are you? Are you 95 confident? You have a 5% uncertainty. So there is no quantification of the uncertainty. And so basically, what is the confidence of the prediction? Secondly, the weights are point estimates. They are obtained by optimization the gradient descent, and they give a single set of weights. And this set of weights might not be the global optima for a small training data. So the first problem is that there is no quantification of the uncertainty in prediction. And the second problem is the weights are only point estimates, which may not be good for small data. We try to address these 2 points in a Bayesian framework. Now let's quickly try to see why Bayesian learning is good for this. We have studied throughout the course that Bayesian learning would give you not a single prediction but a posterior distribution over all the predictions. It is not a single, it's not a point prediction, it's a distribution over this prediction is most likely, this prediction is not so likely, and so on. Similarly, the parameters, let's say the slope of the regression line or the weights of a multivariate regression, the parameters or the mu and sigma of a Gaussian distribution. So these are also not point estimates, unlike maximum likelihood or maximum a priori, MLE or MAP. These also in full Bayesian, these are also distributions. You given a data set, you get a distribution of parameters, that this parameter is most likely fit, this is less likely fit. There is another advantage that you can easily encode your priors. You can easily encode your prior knowledge in the form of a prior distribution in your inference procedure, and this plays the role of smoothing when because your likelihood is based on data and your prior is based on knowledge. If your likelihood is not good because you have less data, you can still use the prior to do a somewhat better job. So priors or domain knowledge can be easily incorporated. This is really difficult in deep learning. You cannot encode domain knowledge except for pre-training or something like that. Okay, so these 2 ideas were merged to form what is called a Bayesian deep neural network. The difference is the follows, that in the Bayesian deep neural network, in the left of this figure, you see a normal neural network where the weights are single point values. Whereas in the right you see, sorry, in the right you see the weights are actually distributions. So maybe the leftmost weight in the hidden and the output layer, it's 0.5, but here it is a peak at 0.5, but maybe also some probabilities in other values. Okay, so you basically in a Bayesian deep neural network, you would have full posterior estimates for the weights. Similarly, you will have full posterior estimates for the output. The advantage is you can have a quantification of the prediction uncertainty. You can account for a distribution of weights rather than a single weight. And this helps, we'll see that this helps when you have less training data. Okay, so let us see how to do this. Let us first quickly review that how a simple Bayesian approach does this. Not going for a complex deep learning algorithm, simple, say linear regression. How does it do it? So let us look at this. Also, I'll give some definitions which are important. So let's look at a simple regression model. I'm trying to predict the output y for a given input x. And the regression model is as follows. Y is some function of x and w, maybe just a linear function w times x, plus some noise epsilon, plus some noise epsilon. Usually, this noise is considered to be a Gaussian with 0 mean, and a white noise 0 mean, and a small sigma square variance depending on amount of noise. So this is and then these are IID. That means every time you, for a different value of x, you get a different value of noise, which are independent of each other. Okay, so in general, in linear regression, it is w times x. In general, it can be some other function of w and x. So we have already done it before. Let us quickly mention it again. So you see the likelihood of a single y given a input value x, given a value of w, and given a value of the noise parameter sigma square, the likelihood probability pyx given x, w, and sigma square, you can derive easily from this. We have already done it before. Is a normal distribution. So y is normally distributed with mean at f of x, w, and variance sigma square. It's a, so y is also a Gaussian whose mean is at f of xw, because f of xw is deterministic. There is no noise in it. Given a fixed value of w, so it is f of xw is the mean of the Gaussian, and sigma square, the noise variance, is the variance in y. Okay, and assuming that each of the x and y are IID and the noise is also IID, so py, the likelihood of the entire set of y in the training set, given the entire set of input x, the weight value w, parameter w, and the noise sigma square, is, since they are IID, is the product of these individual Gaussians. Is the product of this individual. They are independent, so it's the product of this individual Gaussians. So a number of small Gaussians you multiply. So this is my likelihood function, and you can apply the Bayes rule using this likelihood function and some assumption on the some prior distribution assumption on w. Some prior distribution on w, let's say call it pw. It can be something, maybe it's a w is centered at 0, or you prefer small values of w, maybe a Gaussian is the prior. So this likelihood I have calculated in previous slide. In this likelihood I have calculated in this previous slide, and this prior, let's say I assume, and there is a normalizing factor, the evidence, and I get the posterior. So what the posterior says is that what is the probability that w takes on certain value given a set of y, given a training data consisting of capital X and capital Y, and a value of the noise parameter sigma square. Okay, so once these are given, these are observed, what is the, so given a training set, it's the estimate of w in the form of a posterior distribution. So it's not a point estimate, it is a distribution estimate in the point of a posterior distribution, just by applying the Bayes rule. And once you have find pw given y and x and sigma square, you can find the posterior predictive distribution, PPD, just by marginalizing over w, over all possible w. So this is like what you get here is what you get here is a distribution over w given x and y and sigma. You get a distribution over w, and what the posterior predictive distribution does is that you can express py given some input x star and y. So this is a given input. For that I am interested to find out predict y, and this is the training data already given to me. So it is py given x star w, just by the product rule, pw given yx into dw. So I am marginalizing. So look at this term. This is py given the estimate of w and the input x star. This is y, and I weight this by, so if you fix your w, this will give you a single value, a single probability value, or rather it will give you a single probability value, and rather if you look at all y, it will give you a distribution, but for a single value of y, it will be a single value. And this posterior distribution I have already calculated. Okay, so I multiply, I weight this by this, I take the expectation and integrate over all possible w. So suppose this is my value of w, this is my predictive distribution on y. This is my value of W, this is my predictive distribution Y. This is my value of W, this is my. So I take each of these predictive distributions, I multiply by the weights, which are nothing but these probabilities P1, P2, P3. I multiply them by P1, P2, P3 and add them all up. Okay, basically I do in the continuous case, I do an integration. So, okay, so this is very important. So this marginalization or expectation, so I get a distribution, I don't get a 1W. Imagine a regression line, I don't get one regression line, I get a family of regression line, each of which has some probability of being correct. And the final prediction, which regression lines I use all these regression lines or regression lines, and each of the predictions given by each of these lines, I weight them by the probability of each of these lines and add them all up. Basically, I do an integration over all possible values of W. So this gives me, and finally this will give you a distribution over Y, a predictive distribution over Y. So you will, if you add up all these distributions, you will get the final predictive distribution of Y given X star, X and Y, which may be something like this. Okay, so the point to be noted that the posterior predictive distribution is an weighted combination of all possible predictive distributions that one can get by varying the value of W. And this is not just an average, it is an weighted average where the weight is the probability of that particular value of W being correct given the input training data set. Given the training data set, probability that this is the correct value of W. So this term is the weight and this is fixing W, the predictive distribution of output. So this into this weight added up over all possible value of W. This gives me, so this is kind of a, each of W can be thought of as a model. So each of W can be thought of as a model. I am doing an averaging over all this model. So this W would give this Y, this W would give this Y, this W would give this Y, this W is do this Y. I am adding them all up and giving more weightage to the more probable. Say this is more probable, I'll give more weightage to this. This is little less probable, I'll give less weightage. This is less probable, I'll give less weightage. So this is how I'll combine them. So this is the most important thing which is used in deep learning. It's called Bayesian model averaging. On the other hand, instead of averaging, so this is an averaging approach to model construction. Take all possible models, find their probabilities, add them up by weighting them by their probabilities, which is also equivalent to taking an expectation over the thing. But basically, it's an adding up or an integration process. This is one approach of model construction. The alternate approach is once you have this, is this posterior distribution of W, what you can do is that you can do a map. That means you can do a argmax over this. You can do an argmax over this. So that would give you the map approach, maximum posterior estimation. Okay, so mine finds W by maximizing the posterior. Of course, this is an point estimate and this is an optimization approach as opposed to a model averaging approach. So all the deep learning algorithms, they in some sense use this optimization approach. They do an they optimize the posterior distribution, which network best fits the data. Best is the important word. Best fits the data and picked up as a point estimate. And here we are not finding the best data. I am just finding which network, how confident it is about the data, and find out all such networks, maybe infinite number of such networks. And for each of them, find out their confidence. And your final prediction is the average of all these networks weighted by their confidence. This is the basic difference. Okay, so now how do we quantify the, now this is about model construction. Let's come to quantifying uncertainties. Okay, so let us look at the simple regression model, yx equal to f of x w plus epsilon x, where epsilon is additive Gaussian noise. So you see that this w in our approach is not a single point. So w, the posterior of w given x, y given the training set is a distribution. So there is an uncertainty in w. So the flatter this distribution is, there is more uncertainty. The sharper it is less uncertain. And also note that since this posterior is the product of the prior times likelihood, and the likelihood becomes sharper and sharper as your training data increases, as your x and y increases, your likely. So this is likelihood times prior, and the likelihood gets sharper and sharper as training data increases. So your posterior will also become sharper and sharper. So your uncertainty in W will keep on reducing as you increase your training set size. This also actually we have studied long back in the course. But still there is an uncertainty. It's not a point estimate. It's not that W is this single value. It's not this single value. It's most likely this single value, but it might be these other values also. So there's an uncertainty. So since W is uncertain, the first term in so y is a sum of two terms, f of x and epsilon x. So the first term is also uncertain. So if you look at f of xw, you also get an uncertainty here. You also get you cannot pinpointedly say that the first term's value is this, because you cannot pinpointedly say that value of w is this. And the second term obviously is noise, so this is also uncertain. So the total uncertainty in y is the sum of uncertainty of the first term due to w, uncertainty in w, and the second term because of the noise. The first term is called the epistemic uncertainty, whereas the second term is called the aleatoric uncertainty. Note that the uncertainty in the first term, they will keep on reducing as you get more data, and after infinite data it will become a single point. So the epistemic uncertainty goes on reducing as you increase the data. Not only that, so this is a pictorial view. Suppose this is the regression, this is the data. So this is x-axis and this is y-axis, and this much represents the uncertainty in y. This envelope represents the uncertainty. So y might be at this point, y might be this, or this, and these brown points, these are the observed data. These are the training sets. So you see the spread of this line is the epistemic uncertainty. Spread of this envelope is the epistemic uncertainty. You see the epistemic uncertainty varies over different values of x. So here you have no epistemic uncertainty almost. Here you have less epistemic uncertainty. And here you have a high epistemic uncertainty because there is no data there. So this epistemic uncertainty helps you understand where you have a gap in learning, for which set of inputs you have learned properly. And maybe it can ask you to supply more training data in that region. There is no point in supplying more training data in this region. You have to supply more training data in this region. Okay, so there is also another kind of view for this also, which we have studied, is the function space view of this regression. So it's basically your output, your regression line or curve or whatever is a point in a function space, and the Gaussian process defines a distribution in the function space. So these are kind of some prior GP priors, Gaussian process priors, and these are kind of some samples, posterior samples drawn from the posterior distribution in the function space, which you have calculated by multiplying the likelihood with the prior. This is the posterior distribution. The envelope represents the spread of the distribution, and the blue line represents the expectation, the mean value of the distribution. And this shows that it's this entire process of this prediction and then posterior distribution can also be seen as a sampling over some and these are just samples. These individual curves are the samples as a sampling over the posterior distribution in the function space. This also we have extended studied in the Gaussian process, and basically the how good your prior functions are is determined by the kernel function of the covariance function, the kernel function of the Gaussian process, this kernel function k of the Gaussian process. So you took the squared exponential kernel or a Gaussian kernel or a RBF kernel, some other kernel you can choose. Basically it defines the, if you take two xi and xj, how much are they correlated? How much are they correlated? So the kernel function is such designed that if xi, xj are close, they are correlated, and if they are far, they are not correlated. So what is close, what is far is determined by the length factor, the scale factor of the kernel function, and so on. So you can decide. So this is a, so basically if you tune your kernel functions, the parameters of the kernel, you either get a very fast varying function where the window of influence or correlation is very small, or you get a very smooth varying function where the window of influence or correlation is very spread out, very slow. Okay, so one thing, the first use of neural networks, first unification of neural networks with Bayesian learning was happened through Gaussian process. So what they said is that well, the kernel function actually determines what the shape of the function space approximation should be. Sorry, function space regression should be. So, but the shape is kind of given as a prior, as an user input. You fix the shape to be this, the length scale to be this, and you fix that. But there is, it's a hyperparameter. It's difficult to fix that hyperparameter. So why don't you learn that hyperparameter using a neural network? So the kernel function itself is defined as a neural network. It's defined as a neural. So KNN, the kernel function between x and x prime, is defined by this complicated thing, which can actually be derived by this. So as if there is a, you have a kernel function. So what is the best kernel function between xi and xj is computed by a neural network. Is computed by a neural network whose input is xi and xj. Whose input is xi, xj. You give this input, you train a network, this gives you k of xi, xj. Instead of fixing a functional form, you compute it using a neural network. And the good thing is that as and when you train the Gaussian process and you measure the error of the Gaussian process, say log likelihood error or mean square error, you can use the same error function in your gradient descent backpropagation process to train the weights of this network also. So you can backpropagate the entire thing. So this idea was also further evolved into what is called a deep kernel learning. Okay, so it gives you the kind of bias of a deep learning architecture, the flexibility of deep learning architecture, and the guarantee of a Gaussian process. So in fact, it can be seen a Gaussian process can be seen as an infinitely deep neural network. Okay, so this idea was further used. Then after these ideas were developed, people started looking at deep learning from the following point of view. Once they have judged the relative advantage of disadvantage of a Gaussian process and a deep learning neural network algorithm. So this is a nice picture to explain that. So the x-axis is all possible data sets you can get. Okay, so this is, let's say, CIFAR 10, this is, let's say, MNIST, this is, let's say, corrupted CIFAR. So the all possible data sets that you can get hypothetically varies around the x-axis. And in the y-axis, we plot that give the data likelihood. That means if you, what is the likelihood that the CIFAR 10, this point gives you the likelihood that the CIFAR 10 has been can be generated by your model. Okay, so what is the probability that the CIFAR 10 is generated by your model? That is the y-axis. Naturally, this will be a function like this. So if so suppose I fix your model to be this green thing. So CIFAR 10 gives me this likelihood. Maybe there is some other data which gives me likelihood. So your model is probably best for this data and not so good for this data and not at all good for this data. So each of these curves, this green, pink, and this blue curve, gives you one particular model M. Now let us look at three broad classes of models. The one on the rightmost, this blue thing, it's a simple model with a very low inductive bias, say a linear function. So what it will do, there is some simple data for which it fits very well. There is some simple data where it fits very well, but it does extremely poorly for other data. So you have a sharp distribution here. And also it has a small support. It has a small support. It only works for a few number of data, and even among this few number of data, it works on a very small subset. Whereas if you take an extremely complex model like a very deep multi-layer perceptron, it doesn't have any inductive bias. It can fit almost everything. It's an universal approximator. It can fit almost everything, but none of them it fits very well. None of them it fits very well. So the height of this curve is low. None of them, but it has a big support. And it really doesn't do, it's not tuned to a particular data. It can work for any data. And then there is something intermediate, that is this green thing, which is, let's say, convolutional neural network, which is good for, which has a big support, but it's not so peaking, but it has a reasonable, it's not spread out completely thin also. It's not spread thin also. Okay. So probably this green thing is one what you would prefer. Okay, so what does this mean is that if you look at the all possible neural networks in the green model, all possible convolution neural network, and this inside thing is the true model. And what would happen as and when you get more data, so you start with your prior, so this, if you take a CNN prior or some uniform prior over all possible CNN, which is basically the inductive bias, you can fit any data. And as you get more examples, say examples from CIFAR 10, you start collapsing until you get to the true model. Whereas from the linear, you get a small support. And maybe your true model is something here, which is outside your support. So even though you converge first, you cannot really realize the true model. Whereas in the multi-layer perceptron, you have a big support, but your true model is something here, but your posterior doesn't. It takes a lot of training example because it has almost no inductive bias to converge to the true model, which is also an undesirable situation. So there is a trade-off between complexity and flexibility. Okay. Yeah. Any question?
Hello.
Yeah, please.
Yeah. Sir, actually, this question is related to the evaluation of our test. So, just wanted to ask that out
Yeah,
of the.
just wait. I'll answer in the end.
Okay, okay, sir. I'm sorry. I'm sorry.
All right. So let's see how we can solve this previous problem by by using an marginalization or a model averaging approach instead of an optimization approach. Okay. So basically, we'll see how we can apply Bayesian model average to deep neural networks. Let us examine one more phenomena. So this is the error function fx. This is the error function fx along the y-axis, and the training epoch, or rather the weight values. So as you go here, you get different weight values as you move along your training epochs. As you increase your training epochs, your weight value changes. And if you look at the error function, two kinds of error. This solid line is the training error and this dotted line is the test error. You see that two kinds of thing can happen. One can be you can have a shallow minima, you can have a flat minima, and which usually happens earlier in the training. And your test set and training set are more or less close there because it is flat. But in the later of that part of the training, sometime you can have a sharp minima. Suddenly that error falls. And maybe if you train little more, you start overfitting, the error starts going up again. Okay, so you can have a sharp minima, and the disadvantage of the sharp minima is that your training test error minima may be slightly offset from this. So if you set your weights to be here, even though your training error is less, your test error might be pretty high. Okay, so this is what is observed, and this observation helps us in devising Bayesian model averaging in a deep learning network. Okay, so this surface of the error in the y-axis and the weights, different values of weights in the x or more number of axes is called an error landscape or an error surface. So let us examine the error surface or the loss surface. So one phenomena that is observed in the loss surface is that often in the loss surface there are 2 points which have low error, which are minima, and they are connected by something called a mode connection over a smooth path. Whereas if you take 2 points here, if you expand them, if you take 2 points here, it would be a very rugged path from here to here. But here there is a smooth path between two minimas. This is a particular phenomena in the flat region of the solution. So if you have already gone to a flat minima, you cannot do it for a sharp minima. If you have gone to a flat minima, your many of these points here are have a smooth path between them. So in the other word, if you do a gradient descent and you look at the weight values at every point in your backpropagation gradient descent, your weight values will move from here to here. Will keep on moving from each of these points. So if you take a snapshot of your weight values at different points in iteration of your gradient descent, in the error landscape, they will represent a trajectory like this in the smooth region. And if this is done for a sufficiently long time, these points are a MCMC Markov chain Monte Carlo sample of the error surface here, of the error distribution. They gives a Markov chain Monte Carlo sample from the for the error distribution. And they can be used, as you know, that Markov chain Monte Carlo can be used in approximating posterior distributions. These samples can be similarly used for approximating posterior distributions. Here is another example. So this is a mode connectivity here. Okay, so if we look at the gradient descent trajectory, actually not simple gradient descent, if you look at the stochastic gradient descent trajectory and consider every point along the gradient descent trajectory, they are not that, see, this is an error surface, but every point here is a point in the weight space. So if we can fit a posterior predictive distribution, they should give a high value here, because this is an minima of the error surface. I want your posterior to be centered here. Okay, so the weight posterior should be a distribution which is localized in this region. And I want to approximate this from these samples which I have drawn from the HDD trajectory. Okay, so but this you can do not in any part, but in the flat region of the error landscape, in a flat minima of the error landscape. So this approach, this has been actually theoretically proved, is called stochastic weight averaging, or SWA. People actually went one step ahead. They said that why just do an average over all these points? Assume that individually they follow a small Gaussians, and your individually here it's need not take just the average. Assume it to be a Gaussian, and using these samples estimate the mean of the Gaussian as well as the variance of the Gaussian. Okay. So W is a Gaussian. So stochastic weight averaging using a Gaussian is called the SWAG algorithm. Algorithm is like this. If you look at this curve, you vary your training rate, you keep it high, then reduce it, and after some number of iteration, you go to a flat minima. Almost all of that neural network it happens. Then take a snapshot of your weight values, W1, W2, W3, WT. Take a snapshot of your weight values. They will give you a distribution. And from this snapshot of these weight values, you calculate the mean, which is simply over say t number of, you observe, take the snapshots capital T number of times. So the average weight of this distribution of the posterior, so W, it's like this. So let me try to visualize. This is W1, this is W2, and this is my error surface. I go to a flat region. I take some samples here, and I say my posterior distribution on W, PW given X and Y, is a small Gaussian here in this flat region. So remember, in normal neural network, you are just returning a point solution. You are just returning this W. Here I am returning not this W, I am returning this distribution over this W, which is centered around here with some variance. Okay, and the variance is this, you can derive. Variance is this. For more details, you can read the using PCA, reduced it to a small dimension and then plotted the trajectory. There is another way of doing this. So this is over, I have used the stochastic gradient descent and used it to sample over W and used that to construct my posterior over W, which I assume to be a Gaussian. There is another approach to do model averaging. And okay, so finally, how I do? What I do is that when I finally use the neural network, I do a model averaging. I don't use a single neural network. I use a set of neural network with their weight values sampled from this posterior distribution. Okay, I use this net. So each of these are small networks. Each of these are possible networks. So I use an ensemble of, not ensemble exactly, I use all these networks to do my prediction and then do a model averaging over them with the averaging weight being calculated from this posterior probability. There is slightly alternate way of doing this is that, which is also very popular, suggested by Zubin Garamani. It's called a Markov chain dropout. Dropout, as you know, that in really large networks, you sometimes sort of silence some of the nodes. Okay, in some iterations, some of the activation of the nodes are not computed; they are silenced. So this has actually be shown that if you do this randomly, your final network you get is kind of an model averaging or average. So each of the a particular network. So I have silenced this node. This is a particular network. I have silenced another set of nodes. I get another network. Okay, and these are my possible models. And what this dropout along with stochastic gradient descent does is that the final output after your training is over you get is kind of a Bayesian model averaging over all these models. This can be shown. Okay, I'm not going into detail again. You can read this very famous Garamani paper. There is one more way people have used it. I have so far talked about only model averaging, how to fit a distribution over W's, the weight, network weights, rather than a single weight. And one more thing you can do in a Bayesian approach is to use a prior over the weights. So this also people have used a lot. People have defined deep image priors. And the view is that all this pre-training that you do, so often you do pre-training, these pre-trainings are nothing but defining priors over the weight space. This does defines a prior over the weight space. But people have handcrafted also. People have defined deep image priors. People have defined random network features, which is also a regularized prior. So these kind of things have been used. For more details, you can read this paper, Bayesian Deep Learning. Okay, so in summary, the defining feature of Bayesian method is marginalization rather than optimization, as opposed to standard neural network. In deep learning, this model averaging is even more relevant because the stochastic gradient descent over the loss surface gives you this natural Markov chain Monte Carlo sampling. In practice, now Bayesian methods are giving better results than classical training without significant overhead. The cost of this swag are very less. There's a little bit overhead on, very little overhead on the standard deep learning. And this can give us theoretical insights on the construction of so for example, say dropout and other things. There are many toolboxes for probabilistic programming which supplies all this Markov chain Monte Carlo. Note that I've talked about Markov chain Monte Carlo. You can also do a variational inferencing on deep Bayesian networks. All these tools are provided. You have good libraries from them. PyMC3 is a very popular library for Bayesian machine learning. It is easily integrated with PyTorch and other things, so you can use it. RViz is also a Bayesian model library for this model checking, everything. TensorFlow probability is a library for probabilistic reasoning. You can easily, and this is integrated with standard TensorFlow. You can do your gradient-based inference, differentiation, scalability is ensured because of this GPU parallelization. So all these are integrated, and it's becoming a very popular paradigm. So with this, I thank you. And in the next class, I will just summarize. So this is the end of the theory part that I wanted to cover.